Today we'll discuss the Clifford Algebra construction, which is related to the scalar constructions that we have briefly discussed last time. So, a more familiar way to build the scalar representations is through the explicit construction of the Clifford algebras. So, the larger Clifford algebra are constructed by considering the direct product of Pauli matrices. So, you can understand the Pauli matrices, we can see 2 by 2. Now, if you want to go for higher dimension space, then like 4, 6, and so on, then basically you have to take this direct product of these Pauli matrices. So, when you say the direct product, but what do you mean? Like you can think of this M, N, P, Q are the matrices, and you take like M direct product N times the P direct product Q will give you basically NP matrix product times the direct product of the NQ. So more clearly, it is visible in terms of the power matrices like sigma 1 times sigma 3. So you know sigma 1 is basically 0, 1, 1, 0 is the 2 by 2 matrices. These are each basically 2 by 2 matrices, but when you take a direct product, you will get a 4 by 4 matrices. And then sigma 3 will be multiplying each element of the sigma 1, and that's why they are getting this particular form. And so as the sigma 2 direct product sigma 3 is like the 0 minus I 0 is a sigma 2. So this is the structure of the sigma 2 direct product sigma 3, which is a 4 by 4 matrix. Now let's follow the construction procedure, how we proceed step by step. First, we start with the basic 2 by 2 matrix form, and then we define this gamma 1 as the sigma 1, gamma 2 is the sigma 2, and gamma 3 as the minus I times product of sigma 1, sigma 2, and if we do calculate this thing, we get sigma 3. So in 2 dimension, we get this sigma 1, sigma 2, sigma 3, or rather gamma 1, gamma 2, gamma 3, which are basically 2 by 2 matrices. Now, we can multiply this gamma is by the sigma 1 and add one or identity 2 by 2 identity matrix along the sigma 2, and then you find this 4 by 4 Clifford matrices. For example, like in fourth space, we get this gamma 1 as sigma 1 direct per sigma 1, gamma 2 as sigma 1 direct per sigma 2, gamma 3 as sigma 1 product is sigma 3. So is that the first three? The fourth one is basically sigma 2 is extended by this identity matrix, which is also a 2 by 2 matrix. Now, once you construct this thing, then it's very interesting to find out that if you take a product of these 4 gamma matrices, like gamma 1, gamma 2, gamma 3, and gamma 4, which you define as a gamma 5, which takes this particular diagonal form. And remember, this actually diagonal form is not the unique way. It's like a choice of basis or the choice of representations we are doing. Later we will make a big comment about this thing, that one can choose a different basis or the representation of the gamma matrices where this gamma 5 may not be diagonal. But in this particular representation, we have chosen that the gamma 5 is diagonal. And this is nothing but the sigma 3 times the identity 2 by 2 matrix. Right? In this construction, all the Clifford matrices are Hermitian, and we take their bilinear product to give the SO4 generators, and that's what we have understood. Right? So you have the Clifford generators, you take a bilinear combination, and that's what we get the SO2 plus 1 generators. So we have the Xij is minus I by 4 gamma I gamma j, which is nothing but half times identity times sigma k, where ijk runs from 1 to 3 cyclic notation. And X4k is basically minus I by 2 gamma 4 gamma k, which is minus half sigma 3 sigma k. So in this way, we can construct the generators for the SO4. From there, we can construct some kind of combinations, which we define as the LK plus minus, which is using the Levi-Civita, we can define some kind of dual of the X generators. For example, like half epsilon ij k xij plus minus xk, and that is like half 1 minus plus sigma 3 times the sigma k. And interestingly, these generators actually commute with one another and form these two SU2 Lie algebras. For example, LK plus having the structure like 0, 0, 0 sigma k, and LK minus is like sigma k 0, 0, 0. So this SO4 Lie algebra is actually a semi-simple one, and they can be written as a sum of two SU2 Lie algebras. We can also define the operators like P plus minus, which is like half half times 1 plus minus gamma 5, and gamma 5, that is what we have defined as a product of this gamma 1, gamma 2, gamma 3, gamma 4, and that satisfies the projection of operator relations. For example, like p plus minus times the p plus minus is the p plus minus, and the p plus minus times the p minus plus equal to 0. So because of this property of this p operators, so what we can do actually, we can split the 4-dimensional space into two parts. So since they commute with the SO4 generators, so this 4-dimensional spinor space is basically reducible in terms of two-dimensional space, and that's very interesting feature. However, the full 4-dimensional space is needed to realize in the SO5 generators, as we need to add, for because we have a SO5, so we have these extra addition generators in the form of like S45 is minus I by 2 gamma 4 gamma 5, and XI5 as minus I by 2 gamma I gamma 5, showing that SO5 has a 4-dimensional invisible representations, unlike the SO4, it cannot be split into two-dimensional representations. So we repeat the procedure to build 8 cross 8 Clifford matrices by multiplying the 5 previous matrices by sigma 1, and similarly adding 1 or the identity along the sigma 2. For example, like gamma 1, you can define like sigma 1 plus sigma 1 plus sigma 1, and so sigma 2 is basically sigma 1 times sigma 1 times sigma 2. Sigma 3 is basically sigma 1 times sigma 1 times sigma 3. Gamma 4 is sigma 1 times sigma 2 times identity. And gamma 5 is sigma 1 times sigma 3 times identity, and gamma 6 is sigma 2 times identity and identity. Okay. And one more, by taking their product, we can define, which is defined as a gamma 7, and which is minus I times product of all these gamma 1 to gamma 7, sorry, gamma 6, and that is written as a sigma 3 times identity. So this is actually mimicking the structure of the earlier in the 4th dimension also, right? So this is the way we can proceed in a cascade, and we can construct the higher and higher dimension Clifford algebras. So this implies that we can represent both SO6 and SO7 Lie algebra in this 8-dimensional space, okay, using the position operator p plus minus half 1 plus minus gamma 7. But we have to remember that in this position operator can split the representations into two equivalent to same dimensional representation only for the even dimension. So this gamma 7, we cannot have this thing, gamma 7, and we can 1 plus minus gamma 7. This kind of p plus minus operator cannot split these 8-dimensional spinors into two 4-dimensional spinors for SO7, but certainly that can do for the SO6. So now the 15 SO6 generators are, why 15? Because that for SO n, the number of generators n into n minus 1 by 2, so 6 into 6 minus 1 by 2 is 15, so there are 15 generators. So these 15 generators can be written as like xij minus I by 2 gamma I gamma j, where I is not equal to j, and they run from 1 to 6, which are basically 8 by 8 matrices, but can be written into two 4 by 4 matrices in a block diagonal form. And since the gamma 7 is basically diagonal, so you can project according, right? Because they can act on this thing. So thus SO6 acts independently on two 4-dimensional spinors. So basically you can start with like 8-dimensional spinors, you can split that into two 4-dimensional spinors, and the generators which will act on the states or the spinors, okay, so that you can write in the block diagonal form, which is 4 by 4 block diagonal form. So in this way they can act suitably and independently, and this is actually tells you that why the SO6 and the SO4 have a similar kind of Lie algebra. Now, they must correspond to its 4-dimensional complex representation and its conjugate, and that's quite obvious from the earlier one. So now let's take a very interior look, the detailed look of these representations. So we can think of like infinitesimal changes in the form, and like if you have this exponential part, and if you expand that I by 2 omega a lambda a 0 0 lambda a tilde acting on the psi chi, right? The a runs from 1 to 15 because you have the 15 generators, right? But the psi and chi are basically 4 compound spinors because you have split out in these two things, and of course this lambda a are the usual 4 by 4 matrices. You can think upon this way as you 4 generators, and lambda a tilde are closely related as it is only rotations containing gamma 6 that act on psi and chi with different sign. For example, the diagonal generators corresponding to omega 3 is same on both spinors, like half x12 plus x34, which is lambda 3, 0, 0, lambda 3. The generator corresponding to lambda 8 is different. How? Because lambda 8 will differ, which acts on the side, is 1 by twice root 3 x34 minus x12 plus 2 x56. That you can consider. But lambda tilde is not exactly same, but here you can see the sign difference in the x56 associated with the gamma 6. Okay, that will act on the chi. Now one can show that this lambda tilde is basically written as a minus c lambda star c inverse, which we can further write as a c lambda hat c inverse. And this lambda hat is the representation matrix on 4 bar, or the conjugate representation, and 4 by 4 charge conjugation matrix C is written in this particular form. So this is a 2 by 2 block diagonal form, which can be written as I sigma 3 times sigma 2, or is in a, or altogether also you can write down as an 8-dimensional representation, like I by 2 1 minus sigma 3 times sigma 3 sigma 2 and so on. So in this way we can define the charge conjugation matrix in different dimensions using this Clifford algebra. Now the question is there a direct way to see how the conjugation arises? So our Clifford matrices are basically manifestly Hermitian, but not symmetric nor real. So note that the Clifford algebra is equally satisfied by the transposed and compressed conjugation of the matrices, like plus minus gamma I transpose and plus minus gamma I star. So there exists a similar transformation, which is the gamma I. You can replace it by S gamma I S inverse, where S is the semi-transformation matrix. And this preserve the Clifford algebra, and they can be used to change the representation. For example, we chose to work with gamma 2n plus 1 to be diagonal. As I told earlier, that it's not necessary that gamma 2n plus 1 will be diagonal, but we can choose the representations. Okay, so where the gamma 2n plus 1 will be diagonal. If you are not in that diagonal basis, then you can do a similarity of the matrix and you can transform them into a diagonal form. So the conjugation of spinors is basically very tricky. The SO3 spinor representation is pseudo-real in the sense that it has a charge conjugation operator, which is C equal to sigma 2. But interestingly, this is also a part of the algebra, and that's why it is actually the outcome we get for the C2 is a 2 and 2 bar are the basically equivalent, are the same. Same is, but one has to recall that 2 bar is not the 2 star, it's basically I sigma 2 2 star, right? And that's why this conjugation matrix sigma 2 is part of the algebra, and that ensures that 2 and 2 bar are basically the same equivalence. Either you work with 2 or 2 bar is basically the same. Now, these examples suggest a recursive construction of Clifford algebra in higher dimensions, given that 2n minus 1 Clifford matrices 2 to the power n minus 1 times 2 to the power n minus 1 dimension gamma I tilde, we can build 2 to the power n times 2 to the power n Clifford matrices as follows. Like gamma I is basically sigma 1 times sigma I tilde, where I is like 1 to up to this 2n minus 1, and then gamma 2n is basically sigma 2 times the identity matrix. Addition gamma 2n plus 1 is basically minus I to the power n, and then the product of those gamma 1 to gamma 2n, which is effectively at the end of the day sigma 3 times the identity matrix. So these 2 to the power n times 2 to the power n dimension matrices we have, and this gamma A will satisfy the 2n plus 1 dimension Clifford algebra. And that is basically your gamma A, gamma B. Anti-commutator is twice delta B, where A B runs from 1 to this 2n plus 1. So now the 2n plus 1 generators can be written as 2 to the power n times 2 to the power n matrices, like XAB as minus I by 2 gamma A, gamma B, where of course A not equal to B. And by forming the projection operators out of this 2n, gamma 2n plus 1, we can split this 2 to the power n dimension spinor into 2 to the power n minus 1 dimension spinors that transform according to SO2n. So in even dimension, there are 2 spinor representations, but in odd dimension, we have only 1. That's very important thing. And that was related with the somehow when we discussed the chiral formula and all those things. This is related with this thing, why we can define the chiral formulas in the even dimension only. Now, the product of two SO3 spinors yields a triplet, which describes a vector in 3 space and a singlet, right? So the outer product of two compound spinors psi and chi is a 2 by 2 matrix, which can be written as a linear combination of the 3 Pauli matrices and the unit matrix, like psi chi transpose. You can write an identity P naught plus sigma and gi. And in this way, using the trace, we can actually calculate this coefficients Bj. And this is somehow called the Field's expansion of the scalar products. For example, let's consider the scalar representation of SO6, where 4 cross 4 equal 10 plus 6, 4 cross 4 bar is 15 plus 1, 4 bar cross 4 bar is 10 bar plus 6. Now here, of course, the 6 is a vector. Okay, 15 is the rank 2 antisymmetric tensor, and you can check actually rank 2 antisymmetric tensor. If you calculate, then the number of real elements you will get, that's 15, and that's why the dimension is 15. But the third rank antisymmetric tensor Tijk has 20 real components. That's the type of 20 real components. Okay, so now how to get this 10 and 10 bar representations? So for that, what we will do actually in SO6, there is a Levi-Civita with 6 indices, epsilon I, j, k, l, m, n. Okay, like 6 indices Levi-Civita. Now we can define a dual of this Tijk as T tilde ijk 1 by 3 factor, which is normalizations, epsilon ijk lmn T L M N. And then we can define T plus minus ijk, which are basically conjugate to each other. So we have T ijk plus minus T tilde ijk. And similarly, so now you can see this is the way we can define this 10-dimensional representation, 10 and 10 bar. Similarly, we can use Levi-Civita to rewrite a 4-component antisymmetric tensor in terms of a second rank tensor as well. And we can construct the different representations which are not directly connected with a specific rank tensor. Their particular combination we can construct.